of Berlin. It will be about active motion under external fields of collective dynamics by Holger Stark. Please.
Yeah, thank you for the introduction. And I also thank the organizer for giving me the chance to present my research here, or actually the research of my group. And I will mainly talk about work by Oliver Pohl and Andreas Zöttl, two PhD students. And I have to say I'm very pleased to see so many people from the liquid crystal field, which have this neighboring workshop here. And I apologize to Randy, who is giving the talk just at the same time as I am giving here. So we are all here experts on active motion. I'm not attempting to give you a general introduction to that field, so this will only be a very personal introduction, what I am fascinated about at the moment. So we are fascinated about these swimmers in nature. These are two very nice pictures here from the Cambridge group. But we are also fascinated by producing these swimmers, in artificially producing them. This is the famous Dreyfus swimmer. This is a Janus particle. I'm pretty sure we will hear more about these particles. They are just self-propelled particles which swim by a certain mechanism. Another interesting topic here is collective dynamics, and I just copied this. Could have copied other pictures. This is out of the work from Cambridge, Oxford, Düsseldorf collaboration about bacterial turbulence. But there is more to active motion. Active motion also, because it's out of equilibrium, it brings new generic features. For example, that's a work from the Lyon group around Liederich, Bouquet. He showed that active particles just form a normal sedimentation profile, although the sedimentation length is increased. But there is even more to it. One can show that active particles also have to show then a polar order in sedimentation field. When you make these particles bottom heavy so that they are actually aligned upwards, so they want to swim upwards, then you can create these inverted sedimentation profiles, and they are not stable if they become denser and denser. Hydrodynamics actually makes them unstable, and you see these blooms, which has some reminiscent of bioconvection. On the other hand, you can look at swimming under confinement in Boissy flow. That's what I also want to do. This is an artist's view of a blood vessel. That's of course too complicated for us, so we take microfluidic channels as a typical system to study confined motion, and then maybe in the future one can also look at these micro machines swimming along blood vessels or other routes in your body. Okay, so what interests me here is a whole list of questions. So first of all, everything happens here out of non-equilibrium. So I'm interested in finding new generic features of this active motion. I'm interested what external fields to do to active motion and what the collective dynamics is. And on the other hand, we model basically single microorganisms, how they swim. So we want to understand how they swim, but we also want to think about active swimmers, how they function. And from our work, I have taken 3 topics. I want to tell you how a microswimmer in a Boissy flow behaves. I want to give you very generic features, what can happen when you put a swimmer into Boissy flow. And then ongoing work, topic 2 and topic 3, I want to talk about collective dynamics. Everyone is now interested in the collective dynamics of spherical microswimmers, so-called squirmers. They are also famous here in Cambridge, in the group of Pedley and with Ishikawa. I want to tell you basically, that's my opinion, that hydrodynamic matters, at least in what I'm doing here. And then I want to talk about non-equilibrium cluster formation. That's a work motivated by the Lyon group. And I want to understand what they see, that's dynamic clustering. So let me start with swimming in Boissy flow. So in the first round, we take a very strong Boissy flow, so we can neglect wall effects, and then all what you do when you have your Poisson flow, you have a swimmer starting here. It has a direction E and a velocity v0, which is constant for our case. And then you swim basically into the lower half of the channel. Because there is a vortex, it drives the swimmer back to the center line. It passes the center line, and then it's again driven back. And when you just find out what the angle psi, how it behaves according to this nonlinear pendulum equation. So this is the frequency squared with which the swimmer basically oscillates around the center line. So what we here have is basically a Hamiltonian system. You can also show that in 3D you can map this problem on a Hamiltonian systems and find also some conservation laws. You can also now plot phase portraits. So that's the x-coordinate versus the angle. You see the typical phase portraits of a pendulum. So with increasing flow field, you get this closed circles, which give you a swinging motion. You get these closed circles in the channel, but you also get this tumbling solutions where the pendulum makes this here. So let me show you how that goes. I mean, it's pretty simple. You start here. Basically, your swimmer is directed against the flow, and then basically it makes this nice oscillating motion against the center line. If you start outside the separatrix here, when you start with the flow, then you get this nice tumbling solution. As I said, it depends on the turning over solution of the pendulum. Okay, so the question is, do you see that somewhere in the system? And we are working here with experimentalists from Würzburg and Göttingen and Basel. They work on African trypanosomes. African trypanosome, that's a microorganism you don't want to meet actually, because it causes the sleeping sickness. It has this long spindle-shaped shape, and attached to it, I hope you see it, there is a flagellum. It's a typical flagellum as you have in a sperm cell. And this flagellum beats because it's attached to the body. That's a simulation which we do. Of course, the whole swimmer deforms. But even this swimmer here, when you now put it into a microchannel, and in the immobilized, when you immobilize it, so when it's dead, more or less, in the microchannel, then it just flows along the lines. But when it's living, it forms these nice oscillations here around the center line, which I just explained to you. And you can make it more quantitative. That's the swinging frequency of the swimmer, of the trypanosome, versus the square root of the flow strength. So you would expect an immediate proportionality of these two quantities, and you see it fits very well. There's some deviations. What we have to do is we have to take into account that the swimmer is a little bit more elongated, it's not spherical, and then you have to also include these terms which we know from the Jeffrey orbits, so that basically you get also a change of the orientation due to shear, due to local shear, not just vortex, fluid vortex, but also due to shear. Okay, so the next point is what happens when we bring in interactions with our surfaces. So we have a force-stifled swimmer here. That's the simplest approximation of a swimmer. The flow field decays with 1 over r squared, and you have a puller or a pusher, and I don't have to explain what that is. And then when they come basically close to the wall, you have to satisfy the boundary conditions. So you have to introduce image swimmer, as these people have done here, and then you get, from the image swimmer, you get a wall-induced velocity, which you have to add to the swimming velocity, and you also get a wall-induced angular velocity. And so with this analytical expressions, we studied the swimmer in a two-wall geometry, and this is what comes out for the pusher. Now you have to distinguish between pusher and puller. So this happens to the phase portrait. So the tumbling motion no longer exists. It goes towards a limit cycle. That's the green one, which means you have a stable swimming motion with a certain amplitude. And also when you are swimming along the center line, it also goes towards a stable swinging motion. We also did simulations with the squirmer. I will explain the squirmer in a few minutes. So here is how it looks like. And when you do that, when you do the simulation, now in a cylindrical geometry, you get the same behavior basically. If you do that, the whole thing for a puller, so now it's different. You have a stable limit cycle, which is a tumbling motion, but and then you have a separatrix, and within the separatrix, all the trajectories go towards a stable swimming along the center line. And again, simulations with our MPCD method gives the same behavior. So you can say you can use that for hydrodynamic focusing. Okay, you can go on with the system. We heard a little bit about chaotic or nearly chaotic motion. So here you have a system which really very easily becomes chaotic. So what you need is an elliptical cross-section here. This is for the x-coordinate, that's a quasi-periodic behavior, which you see. But when you now increase the flow strength a little bit, then you see this typical signature of chaotic motion. So two trajectories which start nearby, they just diverge. You can calculate Lyapunov exponent, the Lyapunov exponent, and you see there is an onset of chaotic motion, which you also see in the Poincaré section of our four-dimensional phase space. This is the quasi-periodic motion which you see here, but outside of them you have a typical signature of chaotic motion. So that gives you basically an impression. Even such a simple system as a swimmer in a Poisson flow is already a highly nonlinear dynamic system. So let me come now to a second question, and Ray already mentioned it in his talk. There's this big question about is hydrodynamics important for collective motion? And certainly there is no definite answer to that, but at least I can show you a system where I can show you that it is indeed important. And so I want to talk about the collective dynamics of spherical microswimmers. And I want to restrict, because I have to restrict, there is so much work in the literature, I want to restrict to 2D. There is this nice work by the Lyon group and also by the New York group, where they look at dynamic clustering in a dilute system of swimmers. You see dynamic clustering, I show you a movie soon, which is induced by phoretic forces. So some certain attractions, I will talk about it in a minute, or later, some attractive forces which somehow make them move together. Another system in 2D was created in Göttingen in the Herminghaus group by Shashi Tutupali. They have emulsion systems which are very nice swimmers, actually real realizations of squirmers, and they form also these coherent structures here. On the theory side, so this is the experiment. On the theory side, basically people do Brownian dynamic simulation, at least on the particle level, not on the continuum level, on the particle level. So you see, for example, Brownian phase separation here. You see crystallization with jamming, or you see active jamming induced by the boundaries basically here. So what is the influence of the solvent here in these things? Because here in the theory, so far, it's completely neglected. And to investigate that, we take our model swimmer, that's the squirmer. The squirmer is motivated by, for example, this paramecium. The paramecium is covered by hairs, little cilia, and they all move basically in a coordinated fashion, so that you see these metachronal waves running along the surface. And these metachronal waves, they push basically the fluid along the surface of the paramecium, and this pushing of the fluid pushes actually the paramecium forward. So Lighthill and Blake were interested in studying this, and they introduced basically a simple form of this. They called it squirmer. They said, okay, let's basically give the surface velocity at the surface. And the simplest form for surface velocity is a tangential velocity here, and we just restrict to the two first modes. So a sinus theta variation, beta B1 determines the swimming velocity, and then beta, so the second mode with beta, which determines the type of the swimmer. And I should say that this swimmer is exclusively studied or studied a lot by Pedley and Ishikawa in all different aspects. So this is how how it looks like. For beta equals 0, you have a neutral swimmer. The flow field decays with 1 over r to the third. What we already heard, that maybe the far field is not so important for collective motion. And then for beta negative or beta positive, you get either a pusher or a puller, which are very familiar terms to you. So the realization in the Herminghaus group in Göttingen went like this. They have a bromide water droplet in oil, and at the surface they have surfactant, and the bromide in the droplet basically catalyzes a reaction of the surfactant so that it comes in two configurations. So what you have on the surface, you have a surfactant mixture, and this surfactant mixture gives you a gradient of the surface tension, and this surface tension gradient drives a Marangoni flow close to the surface of the droplet, and this is the surface velocity of the squirmer, and this drives the whole system. We have modeled that using some free energy of mixture and some diffusion reaction advection dynamics for the order parameter of the mixture, and we can actually identify different regimes and also map out a phase diagram. So coming back to the squirmer, in theory there are a lot of studies by Pedley and Ishikawa. This is one study where they created a monolayer, but otherwise in a 3D bulk system, and they show basically that one sees coherent structure formation. Okay, unfortunately, this monolayer is unstable, so it becomes unstable. So what we do is, so we study squirmers in a quasi 2D geometry, and so this is the geometry. So the thickness of the layer is a little bit more than the diameter of the spheres. This is a top view here. We have 208 swimmers, and these are our parameters. This is the areal density, which has a range from 0.1 to 0.83. And then we determine the fluid motion around the squirmers. And we do that with a method called multiparticle collision dynamics, which I don't want to explain at all here. It's a particle-based method, which is used, for me, it's basically a solver of the Navier-Stokes equation in a very rough manner. Okay, so this is the multiparticle collision dynamics. You can couple the squirmer to these particles or in this simulation method by appropriate boundary rules, and then we also invoke periodic boundary conditions here. So let me now show you what happens with our system. So this is a low volume density or areal density, and we are basically here in a gas phase, a neutral swimmer, and you see this is the velocity distribution. The maximum is close to 1. So these are our swimmers, and they are, of course, they collide with each other, and a little bit that they get deaccelerated in their velocity, but nevertheless you get this broad velocity distribution. On the other hand, if you go to very high areal fractions, you get this jammed crystalline phase here. You see that the velocity has shifted close to 0, and then we want to the onset of this crystallization of these packed clusters. We want to notify by a bond orientational order parameter, which tells you if you have basically 6 particles around them. And you see that this bond orientation order parameter is peaked at 1 and also has a little bit of, but no distribution basically at the smaller values. Okay, so now what happens when you go in between? You get, for neutral swimmers, you get a clear phase separation. So that means you get basically packed clusters indicated here by our order parameter, but you also get free swimmers here, where you have basically indicated by where you don't have any bond orientational order. And also the velocity here indicates this is the crystalline phase, and these are the free swimmers. So now the important stuff is, so you have space separation. Now you change basically the local field around the squirmer. you take now a pusher, beta equal to -3, so you set in the second mode, and this is what happens to the system. You can let it run for a while, and you don't see any phase separation. You don't see any significant clustering. Basically, you have a broad distribution in the velocity, but also in your Q6 autoparameter. So what I can say here is that the phase separation is basically suppressed by these local flow fields, because I mean the local flow fields are important here, not the long range ones. So this gives you basically a summary of our color-coded local bond order, just to summarize. So here's the increasing areal density, and here you increase beta. This is beta equal to 0 with the phase separation, and here so at large beta, magnitude of beta, you don't see any phase separation. You can make this more quantitative by looking at the autoparameter Q6 squared, and you average over the whole sample and over different time steps. Here at beta equals 0, you see a typical sigmoidal shape of our autoparameter, and here basically here's the onset of the phase separation, whereas for the large betas here you just have a smooth transition of the Q. And then you also can look at the fluctuations, and exactly at 0.5 you have large fluctuations in your autoparameter. And just to show you how this looks like, this is exactly at this where you might locate the phase separation point. You have these clusters set up, but then they vanish again. So you have really large fluctuations of ordered structures which decay. So I already said this has a lot to do with the local flow field. So one mean to characterize this, and I'm sure there are a lot of other means, but we already also looked at the rotational diffusion. So basically, what is the rotational diffusion of a squirmer embedded in other squirmers? And we refer these values to the thermal value. And what you see here in this color-coded picture, so you see that with increasing volume fraction, or it's actually an area fraction, you get an increase of the rotational diffusion constant, but also when you change your beta, so with a large magnitude of beta, you even get up to a factor of 25 compared to the thermal diffusion of an isolated particle. So that means that, and this is set up by the hydrodynamics of the particles. So basically, here's a particle, it creates a local flow.
Do you also have the thermal Brownian motion in your simulations?
I forgot, I forgot to say that. So in multi-particle collision dynamics, we include actually, this is one of the advantages, you have included the thermal motion. Thank you. So you set up the local flow field, and this local flow field actually drives the nearby particles, and because the motion of the particles is random, chaotic, this gives rise to this rotational diffusion here. So we determine this rotational diffusion constants by looking at the decorrelation of the orientational distribution function. So from this part here, at very high densities for the neutral streamers, we also see a decay here, and we don't know at the moment what that is. Maybe there is some jamming of these particles, but of course this is about rotational motion, so we have to look more into this here. So let me give you again another aspect. So this is what you already saw here, and in addition, Andreas also did simple Brownian dynamic simulations, no hydrodynamic interactions. Here in the lower line, he just took circular disks in 2D, no hydrodynamic interactions, just some sort of a hardcore repulsion. And then here, this is our geometry, two-plate geometry. So you allow these particles, actually, for example, to show rotational diffusion, and you see a very different behavior between these tools. And then, okay, you can basically think by yourself. So this maybe is close to what you see here, but basically what I want to show here is that the setup of the system actually matters. So what you do, you should be aware of what you do, and And this is just shows you there's a difference from here to here. Okay, so this is where we are at the moment, and what we are trying to understand more, what is the influence of these local fields, what is the rotational diffusion doing, how are actually the squirmers, if they are pushers or pullers, they actually react differently in this two-wall geometry. The pullers are more attracted to the wall, they stand up to the wall, so we are currently clarifying all these points.
So if you include hydrodynamic interactions between squirmers, they're going to undergo large orientation jumps when they come near each other. So it would seem to be not like a rotary diffusion process.
Why not?
Because in a diffusion, you would think that it evolves through very small orientation jumps, rather than like, it would be like a Boltzmann collision, like.
I don't think it's everything, all is over damped here, so you still will have smooth variations of the orientation. So you won't get these jumps, definitely not, because everything is over damped, and you are not allowed to think in simple cases of collision, so that you have something like that, and then it makes suddenly that it's all goes smooth.
Yeah, I'm thinking of before. No, I'll talk to you.
Okay, good. I think I still have time. Let me come to my third part, and the third part is motivated by these experiments in the group in Lyon by Liederig's group. They do experiments with active Janus particles. So they have active particles, that means they have gold particles with a platinum cap, and these particles are powered by this reaction where hydrogen peroxide is split into water and oxygen, and then by some phoresis mechanism these particles start to swim. And what the Lyon group has, for example, looked at low volume area fraction, so the particles basically sit close to the surface, so that you have a two-dimensional system. You see this cluster formation. So the clusters are forming, but they also break up again, and this is a very dynamic system. And they even looked at the mean cluster size, and it goes proportional, what they found, proportional to the velocity. I will not come to this point here, but so let's understand first, or shed some light on this dynamic cluster formation in this phoretic systems. And this gives me already the right word, phoretic interactions. So where is this cluster formation coming from? This is the important point. So this is the particle which consumes hydrogen peroxide. So it produces a sink, basically of a chemical. So for the nearby particle, it produces a chemical gradient. And we know from colloidal physics, so this is the relevant literature here, we know that colloidal particles in these chemical gradients, they experience some velocity, or they basically move with a velocity which is proportional to the gradient of the chemical. So for example, this particle would move towards the other particle because we have a negative gradient here. If zeta trans, the chemotactic coupling constant, if this is positive. So you have some sort of attraction between the particles. On the other hand, we know also that we not only have the translational diffuser phoresis, we also have rotational diffuser phoresis. So that means in a chemical gradient, the particle experiences some torque. So E1 is, or EI is the direction of the swimmer. So for example, this here. And in particular, so in the setting which I'm using here, if this coupling constant, and this will be important, if this is negative, so the swimmer here will be directed away from this gradient here, and it will basically swim away from the particle. So you have some two antagonistic effects, basically attraction of the particles, depending on the sign, of course, and basically going away from each other, some sort of a repulsion. And this is what we basically put into a Brownian dynamic simulation, where we simulate this Rorschach equation. So that's the position, that's the orientation, that's the speed of the active speed of the particle, that's the noise here. And these are the two terms I already explained. And in addition, we also introduce some hardcore interaction rule. Simply, when these particles overlap, we just put them apart symmetrically so that they basically don't overlap anymore. So that's a very simple interaction rule. And then we also have the chemical field. So the particles, at least that's what you assume here, act locally as a sink. So they have a source for the chemical field. We neglect any time dependence because we say that the diffusion of the chemical field is so large, or is so large that it basically goes instantaneously. And this is the solution of this to this static diffusion equation. Okay.
Could you remind us what this mu I is in the second?
Sorry.
What is the last term in the second differential equation?
Oh, that's thermal noise. Sorry. Thermal rotational noise. Okay, so now we look for clustering in non-equilibrium. So here we basically have a translational diffusive already coupling, which is 0, and then we get more or less some sort of a gas-like phase with some mean clustering size of 3.3. We start at 3. That's what Litterick was doing. And on the other hand, when we increase this diffusive already coupling, at a certain point we get some chemotactic collapse, some sort of a chemotactic collapse, which is well known from chemotaxis of bacteria. So we also see that here. But when we now look closer in the range between these two cases here, we actually find also this dynamic clustering. So don't look at these mistakes in the movie, but we see this pronounced dynamic clustering. Clusters form basically, and they decay, and this is all very dynamic, with a mean cluster size of 9.5, very similar to what the Litterick Bouquet group observes. And we actually, all these parameters which we have here are chosen close to their parameters here. You can look at the cluster size distribution function for increasing translational chemotactic coupling. So with increasing coupling towards dynamic clustering, the distribution function gets broader and broader. And interestingly, it can be fit by this combination of this exponential decay and power law decay with a constant within the error bars here with a constant exponent q. The n zeta is of course varying. And for the dynamic clustering, basically this part here is determined by this algebraic decay. Then we can also map out state diagrams. So first of all, we have translational coupling versus the Peclet number. We see two pronounced regimes. We see a gas-like regime where the clusters are not formed at all. We see this collapse I've already explained. But this dashed line here, this indicates some transition where these particles, they actually collapse into a cluster, but this cluster is not stable, it breaks up again, and so on. So this is an unstable, this green area is an unstable n-particle cluster, and then only when you go beyond this line you have a collapse. And that all happens, of course, for a constant Peclet number, which I don't have to explain, when you increase your translational chemotactic coupling. And then you also get this dynamic clustering somehow around here. So this is squeezed in between this gas-like behavior and this collapsed state. So now if you fix the Peclet number here, if you fix the Peclet number and you plot basically a state diagram zeta trans versus zeta rot, so these chemotactic couplings for translation and rotation, you can see the gas-like phase here, the collapsed phase, but then you see this green part here. For positive zeta rot, you see some sort of a phase separation. That means the cluster, all the particles, they form a more or less stable large cluster, but you also have you also have a gas phase of isolated particles around the stable large cluster. And if you cross now to negative zeta rot here, you again find the unstable n-particle cluster. So you already see there is a very wealth of phenomena coming up in the system here. and I guess I'm too fast, but then we have more time for discussion. But let me tell you a little bit. So I could end now here, and I'm not sure if you are impressed or not, but there is a subtle effect actually which we need to produce such. I would say for me it's a pronounced dynamic clustering. So remember, we have this chemical field which decays because it's static. It decays with 1/r. So every particle carries around with itself a chemical concentration field which decays with 1/r. If we just do that and also keep these 1/r dependence in the clusters, etc., we don't see this pronounced dynamic clustering. We see clusters which come up to maybe 4.5 or 5, and then we immediately go to the collapse. And this is what we know also from chemotactic collapse in bacterial systems, because there is a lot of analogy what I'm doing here to bacterial chemotaxis, and at least on a mean field basis, on a continuum basis, you can actually have the same equations, like something like Keller-Segal equation, etc., etc. So, but what we have to do is to see all that here is to screen basically when a particle is surrounded by 6 neighbors, then we need some screening. So this particle only interacts with its immediate neighbors and not with other neighbors around it, or with next nearest neighbors, etc. Only when you do that, if we cut somehow this chemotactic or this sporadic interaction, then we see this pronounced clustering, which I have which you see here. Okay, so with this I'm at the end. This is my summary. I showed you that microswimmers in a Poisson flow are already a very interesting nonlinear system with, you can describe it by a Hamiltonian system, which introduces also dissipative dynamics, and then you go towards chaos. I told you that at least in our setting, hydrodynamic matters when you study the 2D motion of squirmers in a confined geometry. And then I gave you some first results on how we study non-equilibrium cluster formation with chemotactic colloids or colloids which interact by phoretic interactions. And I thank you for your attention.
If I understand right, you've ignored the concentration dynamics of the.
Yes.
Is that ever important?
To my understanding, it's not important. If DC is larger, much larger than sufficiently large. But I think it's usually done. For example, also in old work by Brenner, but also he has done it. I think it's a good approximation.
I have a question about the second part. So you have MPCD and then you have these dense colloid suspensions. I was wondering if you study whether there is this crystallization or not. Do you put in lubrication forces by hand, because MPCD usually doesn't resolve them on the scales where they're important?
This is a very interesting point, and we looked about it. Of course, I mean you're right. When they come really close to each other, you have problems that you don't resolve. Seemingly the hydrodynamics. But actually, there are studies by Petley and Ishikawa where they actually tell us how the lubrication forces, how they are for squirmers. And we actually compared this with our simulations, and at least the results are pretty similar. So in a certain place, we get the lubrication forces in our simulations. I don't want to say that they are exact, but it's pretty good.
So I guess following on that question, the question: how well do you think your model deals with incompressibility of the fluid when you get to these very close separations?
Compressibility of the MPCD fluid.
Yes.
This is always a big point. This gas of fluid particles is always, of course, to a certain degree compressible. That's clear. But there is some I would say some common sense of when you look at the Schmidt number, you have to be sufficiently low, and then basically the common sense is that that this is basically enough. I forgot now what the value is.
And does that work when they get very close to each other?
Okay, that's a pretty good question. I have to think about it. But as I said, I mean, with these lubrication forces, we are aware of that, and we can actually not fully quantitatively, but we come pretty close to the quantitative description. So I'm pretty confident that this is actually okay, what we are doing here.
Your phase diagrams remind me of like first order phase transitions. So my first question would be, do you see that as well? Or the second part would be, if you increase the temperature, could you see something like a critical point beyond which the collapse and the gas-like phases are not longer distinguishable?
I mean, I'm a little bit careful of talking here about phase transitions because we are in 2D and everything is certainly more complicated, and we have really just 200 particles. That's why I'm really avoid more or less of talking about phase transitions. So what you see here, what you see in this part is maybe there is some this sigmoidal line which I showed you. This might have a signature of a second order phase transition, but actually I mean the systems are too small.
I would say first order. So
first order.
Because you have a region which is gas-like, you have a region where you have separation.
Yeah. Okay.
And you have a region where it's collapsed. So it's a little bit like a van der Waals gas, where you would have gas phase coexistence.
I know what you mean.
So.
I mean, just we don't see it. I mean, the best what we can do here is, and we also played around with the autobarometers, which we need for showing this effect. And we really find, I always wondered why all the people also, when they look at crystallization, they all use these local bond orientation autoparameters. And we played around with these parameters, and it turns out that this parameter is actually a very good indication. But I mean, this is basically the best what we can do. I have to admit, yeah, we did play around. Maybe when you are right. If we play maybe around with the Peclet number, the Peclet number is here very large. I think it's beyond 100. So maybe we see some more. But at the moment, I wouldn't say I see an indication for a first order phase transition. It's just smooth.
In the third model, if you switch off this diffusive term, this beta, what does your phase diagram look like then? And in a follow-up, in that context, what are the mean field equations when the noise is set to 0?
So now I have to. What do you want to switch off?
So the thermal noise term, the mu I, if you knock that out and you look just at this interaction between the hyperbolic rotational part and the diffusive translation part.
I think then I get some. So we haven't done that. I think you get some, because you need that to produce diffusion. So when you talked about the continuum equation, so you need that to produce diffusion. So I'm not sure if that then the system would somehow collapse, I guess. Well, I'm not sure about it. I can't tell you. If you really switch off the noise, I'm not sure what happens.
And could you remind me what the Peclet number is for this system?
Oh, the Peclet number is the influence basically.
I want in dimensional terms, in terms of the parameters.
We introduced it a little bit more. It's a little bit like the conventional stuff, but we have some average, because they have a strength. Here you get the translational diffusion, and here you get the rotational diffusion constant. And for colloids, they are this, more or less they are just scaled by a radius squared. So basically, it's the normal definition of the Peclet number, basically.
But the concentration of Peclet is 0, right? Because you just neglect all the action during the last equation. You say 1 over R decay of the concentration.
Yes.
Here the Peclet number is like 0.
For the chemical field?
Yes.
Chemical field is just diffusive, so I don't have. There's no Peclet.
Is it justified?
I mean, the chemical field is just the dynamics is diffusive. There is no.
Well, but things move, right? So there's
Sorry?
Things move, and there's attraction associated with this.
Yeah, but there's no. I mean, there is no active forcing of this of the chemical field, and they are not. It's just a diffusive
Purely diffusive.
Purely diffusive dynamics. There's no other question about it.
More questions? Please.
So you had mentioned in the context of defining beta, the slip velocity that's created by a swimming organism. So for large values of beta, the surface velocity reverses sign. Is that right? For large values of beta, the surface velocity reverses sign on the organism, on the sphere.
Yeah, that's right. Yeah, if you make beta large, then you don't have just the sinus.
So is there a physical system that exhibits that character? Because
That's a good point. I think you are right. That's the point. A natural system, I think they tend to have smaller betas. But I can't tell you now what, for example, the squirmers in the Göttingen group. I'm not sure now how large they are. But normally you are right. In all these natural systems, we know they are the beta is not. You hardly come up to 3. That's normally they are smaller.
Questions, please? Okay, thank Holger again.
Thank you.